In this new section, we'll continue to discuss the discoveries from the previous sections, and we'll start right away with two definitions. A set is called countably infinite if it has the same cardinality as n. And we have to introduce a new symbol here. Georg Cantor used the Hebrew alphabet Aleph Naut to describe the size of the set n and the size of any countably infinite set. A set that does not have the same cardinality as n is uncountable, and the first known cardinality higher than Aleph Naut is written Aleph 1. There's a great question that exists in mathematics, and that is, are there any infinite sizes between Aleph Naut and Aleph 1? And it is called the continuum hypothesis. And if you are interested in this fantastic story in the history of mathematics, you can refer to the additional resource article that I shared in the introduction page. So as a reminder, two examples. Z has a cardinality of Aleph Naut, and R is the prime example of an uncountable set with cardinality Aleph 1. So it's very important to note that a set is countably infinite if and only if its elements can be arranged in an infinitely long list, A1, which would be the first element, A2, A3, A4, etc. If you can do that, basically you can pair the elements of that set with the natural numbers, 1, 2, 3, 4, so it will have the same cardinality as n, and therefore it is countably infinite. So in this example here, we will discuss the cardinality of the prime numbers, but the important note above comes up again and again in this section. So what is the cardinality of the set of prime numbers? Obviously, we know there's infinitely many prime numbers. So is it countably infinite or uncountable? Well, since we can just list them, it's possible to list the prime numbers 2, 3, 5, 7, 11, 13, 17, 19, and so on. We can conclude that it's a countably infinite set. If we call P the set of prime numbers, then the cardinality of P is Aleph Naut. So simply because we know that we can list them and we won't miss any, we are confident it's a countably infinite set. If we look at the Venn diagram here on the right, there's a very natural question that arises. On the one hand, we have n and z that are countably infinite. On the other hand, we know that r, the real numbers, are uncountable. So what about q, right? Is it with z and n countably infinite, or is it with r? So this is what the theorem tells us. The cardinality of Q is Aleph Naut. And we will use the fact that we just discussed. We're going to be able to make a list of all the rational numbers in a clever way. And since we can make a list, then we will be confident that it is infinitely countable. So how do we make this list? First of all, we want to have all the integers 0, 1, -1, 2, -2, 3, -3, 4, -4, and so on. And below that, we write all the fractions whose numerator is the number up here. So 1, we have 1 over 1, which is 1, 1/2, 1/3, 1/4, and so on. Below -1, we have -1, -1/2, -1/3, and so on. Under 2, we have 2 over 1, but we don't write 2 over 2. So we want only fractions in reduced form. So 2 over 2 is equal to 1. So we don't write this one because 1 is already here. So we have 2 over 1, 2 over 3. We skip 2 over 4 because 2 over 4 equals 1 over 2 right here. 2 over 5, we skip 2 over 6, 2 over 7, 2 over 9, etc. Same with negative 2. We will skip negative 2 over 2 and negative 2 over 4 because we saw those in the column with negative 1. With 3, we write 3 over 1, 3 over 2, we skip 3/3, which is equal to 1, etc. So you got the idea. And now, with this grid of rational numbers, the great idea is to go around and making sure that we won't miss any, we can follow the pattern that is shown here. This is not the only possibility, but it is one, and it will ensure that we won't miss any number. And basically, this is the first one, A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, and so on. So we have shown that we can make a one-to-one correspondence between the natural numbers and Q, so we can conclude that the cardinality of Q is Aleph naught. Using a similar strategy, we can show that if we have the Cartesian product A cross B of two infinitely countable sets, A and B, so infinitely countable sets, then this Cartesian product is also infinitely countable. So in order to show that, we will once again exhibit a list of the elements in A cross B. The method is similar to the one shown in the previous proof. So it's upside down compared to the previous proof, but if we look here, these are the elements of A. And since we know that A is infinitely countable, we can list them: A1, A2, A3, A4, and so on. There's infinitely many. B has elements B1, B2, B3, B4, B5. And this creates a two-dimensional grid where we can list all the elements of A cross B. We have A1, B1, A2, B1, A3, B1, A4, B1, and here A1, B2, A1, B3, A1, B4, A1, B5, and so on. And maybe you can guess what's going to happen here. We're going to follow the same idea as we did earlier. By zigzagging like this, we're not missing any elements of A cross B, and therefore we can call this the first element of A cross B, the second one, the third one, the fourth one, the fifth one, etc. A corollary of this theorem is that Q cross Q is countable, infinitely countable. So since Q is countable, it follows directly from the previous theorem. It's a corollary, so it follows directly from the theorem above. Let's see another theorem that is interesting when we have two infinitely countable sets A and B. If A and B are both infinitely countable sets, then their union is infinitely countable as well. So what we need to do here is just to figure out a way, we need to figure out a strategy that will list all the elements of A union B without missing any. And there's more than one way to do that, but here's the simplest one. It's the same idea as when you shuffle cards from two half decks, and you just put one card from the first half and one card from the other half, and so on. So we can write A1 and then B1 and then A2 and then B2 and then A3 and then B3, and this will list all the elements of A union B. Now we just have to agree that if it happens that A and B have common elements, then we're just going to skip them. We don't want the same element to appear twice. So to conclude this section, we have a final note that opens kind of what would come later on if we continue to study these concepts. Let A be an infinite set. It can be shown that the cardinality of the power of A is greater than the cardinality of A. So why is that important? Well, it's important because it shows that there are infinitely many infinities that exist. Here's what we can do. The cardinality of A is going to be smaller than the cardinality of the power of A, but itself is smaller than the cardinality of the power of A, and so on, and so on. So if A has a cardinality of Aleph naught, then this could be Aleph 1, Aleph 2, Aleph 3, and so on, forever. So there are infinitely many infinities. Thank you for listening.